Okay, so taking a look at module 8, well, it's basically a pretty sort of broad topic that it more or less encompasses, well, basically structure of atoms and how things came about. So we're looking at, it says from the universe of the atoms, so we're looking at anything from very large scale at the universe sort of level, as well as very small at the sort of atomic level, and your standard model of matter. And it's a very sort of heavy content based part. So a lot of this we'll try to quickly go through. Now, I know some of you are having trouble with this too, in terms of the content. I will try to kind of do what we've done for the other topics and so forth, which is give you the key aspects. The details might be best for you to read over, or if you've got specific parts, then let me know and we might try to go over in more detail. But going into each part in detail will take a sort of a bit of time. And so definitely, do let me know if there are certain parts and we can see if that's something that will help everyone as well. Okay, so firstly, you need to sort of understand where elements come from. And well, essentially that needs us to sort of understand what happens with where our universe comes from and how things sort of started. And so we need to kind of go back to the start of the universe. All right. And you guys hopefully understand that the start of the universe is sort of a Big Bang. All right. And so our theory of the Big Bang is that we had a singularity, and singularity then, started spreading out. And this was all radiation at this point in time. And once this radiation spreads out, it starts to kind of cool down. Okay. Kind of think of it like a gas. I mean, it's not a gas, but it kind of, you're kind of thinking of decreasing the concentration of this radiation. And then as the temperature sort of decreased, basically things that, you could form bigger things, you were able to form bigger things. And so the first thing that was able to be formed is your matter at the most basic level. And that's when we say, we've got your quarks and your subatomic particles. And your subatomic particles, of course, as the temperature goes further, allows you to form your protons. Your quarks can form protons, neutrons, electrons. And then as the temperature dropped a bit further, then you could form your atoms, starting with hydrogen atoms. And that's basically how we're saying our matter came about. We're saying that the start of the universe is sort of a singularity. This singularity was basically pure all energy. Now, this energy then basically sort of expanded out. As it expanded out, its temperature dropped. As temperature dropped, that basically allowed bigger things to sort of become stable, all right? And once it became stable, you started having sort of quarks. Then quarks, once you had more quarks, they could more likely form, protons and neutrons. And once you were able to form protons and neutrons, they could form atoms. And so we ended up being able to basically have all these sort of atoms floating about our sort of universe, right? And, you can kind of think of the reverse, right? Nowadays, if you think about on Earth, we've got, molecules, right? And your molecules can be broken down, right? If you heat it up enough, you can break down a molecule into a more simple molecule. And if you heat that up even more, then it'll become an atom. And if you, heat up an atom even more, then it'll become an ion. And if you heat up an ion really a lot, then it'll, break further down into, protons, neutrons, and electrons. And if you heat up protons, neutrons, and or not so much electrons, but if you heat up protons and neutrons even more, then like we might do in a particle accelerator, then we smash them into quarks. And we haven't really managed to do that, the next part yet, but if we smash them up even more, then I suppose, you know, would make it so quarks can't even sort of exist. And that's sort of part of what we're doing in particle sort of research, right? Particle physics research involves doing those sort of experiments. Okay, and that then, you know, leads us into having these hydrogen floating around. And well, we're basically then going to get the fact that these gases are flowing around. And these gases then, due to gravity, can undergo what's called accumulation. Because remember, gravity pulls things together. And these hydrogen molecules have gas, right? Have mass. And so mass will then just cause these things to sort of clump up. And as they clump up, and obviously we're talking over a long time period here, then they will basically form clusters. So you'll basically get gas just trying to sort of join together to get sort of a, you know, smaller gas until they sort of get closer and closer and closer together. And that's how you start forming, you know, your stars and galaxies. Basically, due to gravity, they will bring them in from the outside. They'll try to sort of, you know, gather everyone in. And you kind of, the more mass you get closer together, the stronger the pull, and the more you will pull everything else in. And that's why all of this thinly spread mass over millions of years and, you know, millions and millions of years then gets then concentrated into, you know, certain areas like a star, potentially, if it's big enough. Okay, so that's our theory for the start of the universe. But of course, we need to examine our evidence. And the evidence of course, one of the biggest key evidence is, well, Hubble's law. Well, we basically, you know, noted the expansion of space. So the short version is basically that Hubble was doing some measurements in the early 20th century. So you have to remember, this is also not that long ago. I mean, it's 100 years ago, but in the context of things that have been studied for, you know, thousands and thousands of years, 100 years ago is not that much. And so Hubble realized that actually, you know, people used to think that everything you look up in the sky was a star, right? Okay, you know, it looks bright, it's a star. I mean, even before that, people used to think that, well, everything was around the solar system. They didn't think there was anything outside the solar system. And, you know, they realized, okay, well, that's not quite true. The star's the only sun in the solar system, and, you know, the stars, other stars are very far away. But Hubble was basically the first person to realize that, well, actually, what I'm looking at is not just a star, but a galaxy that's very far away. So I'm not sure if you guys are familiar with these terms. Hopefully you are. But basically, think of, like, you know, your solar system as your sort of suburb, right? So we used to think everything was in our suburb, and well, no, you've got things that are like, you know, a different sort of city away. So, you know, you've got a different city. So maybe just call it a state, right? So, you know, you've got stars. So, you know, there's lots of suburbs inside a city, inside a state. And so that's kind of your star. And so, okay, we recognize, okay, there are different states. There's New South Wales, Victoria, you know, Queensland. But Hubble was the person who then realized, actually, well, wait a minute, you know, United States. Yeah, it's got the word state in there, but it's not a state. You actually have a country, right? And that's, you know, that's when you talk about galaxies. Right? And so Hubble was the first person to sort of realize that actually, well, this that thing you're looking at is not actually just another star. It's actually an entire galaxy made up of lots and lots and lots of stars. And that is, you know, much further away than anything, you know, than the stars they've been looking at, which were all in the, you know, the Milky Way galaxy before. And what he also noticed was that basically all galaxies were moving away from us. And that sort of suggested that space was expanding. And I suppose, you know, we could sort of try and explain that given what we've got here. So basically, obviously, you know, we live in 3D. But basically, you know, let's say we're here on Earth and we're looking at just, you know, things. Just, you know, these are galaxies or stars and galaxies. And, you know, we measure distances, right? So, okay, the distance there, we've got the distance there. We've got this distance here. We've got this distance here, and so on, right? Each and every distance. Now, what Hubble realized was when we measure these distances, it doesn't matter which direction we look at, right? I can add another one, right? It doesn't matter which direction we're looking at. The distance is always increasing, right? All of these distances are increasing. And so his conclusion was that space is expanding. Now, what does that mean? That doesn't mean that, okay, these things are just moving out. So it's not that these things are just moving out. It's not, we're not saying, you know, that's there, that's there, that's there, that's there, that's there. We're not saying that. That's not what we're saying. What we're saying is, well, this is happening. Okay. So you can see that, you know, compared to before, every line has gotten longer. Because basically the space itself, like this rectangle, is getting bigger. And so that's what we mean by expansion of space. And that is why we're saying everything, you know, is going out, because space is expanding at the galaxy level, right? You might have local effects, you know, within a galaxy or so forth, but essentially, you know, at galaxy to galaxy level, when there's so much free space in between, everything is running away from us. And this is sort of our explanation for it and is part of our sort of evidence. So evidence includes, you know, the fact that galaxies are receding. They are going away from us. And basically we can tell that using our redshift. Right? And again, that ties into a wave theory of the Doppler. Well, it's not really the Doppler effect, but very similar. And the other, you know, sort of key evidence comes from your background radiation. So in very simple terms, we've basically said that the bigger, you know, the bigger you go, the lower the temperature. Kind of think of it like a gas, right? For those of you who do chem, which is most of you, then, you know, think of it like PV equals nRT. As your volume goes up, your temperature goes down, all else equal. And we basically suggested that, hey, look, if you really did start as a ball of, oh, where did everything go? If we really did start as a ball of, wait, if we really did start as a ball of energy and, you know, it just got bigger and things are starting to cool down, then we can kind of think of how big we are now and kind of figure out what temperature we should be at, right? And so we did. And we calculate a temperature of, you know, approximately 2.7 Kelvin. And, well, we then found evidence of this. So basically, I mean, most TVs nowadays are digital, but if you had like an analog TV, so one that sort of just picks up sort of signals in the air and so forth, you'll notice that, you know, if you turn on a TV and it's not digital and it's analog, then you used to have this sort of screen where it will just give you this sort of fuzzy whitewash picture of like white and black. And it gives you that signal because there is noise. And that noise comes from this background radiation. And that noise, you know, because if there's no signal, your TV should just show a blank screen. And that's what digital TVs show nowadays. But, you know, because they can't interpret that noise. But if you've got something that just actually measures the signal and displays the signal, which is what analog TVs do because of by design, without without borrowing, then it will show this sort of fuzzy noise, even when you're not, you know, trying to get to any TV station. And it doesn't matter which direction you point it, you will always get the same noise, which suggests that it does come from everywhere. And that's further evidence for the Big Bang. Okay. And that's basically your collection of the Big Bang theory. Now, you'll need to know sort of, therefore, the next thing we need to basically talk about is how, you know, your stars get their sort of energy from, or where they get their energy from. So you might need to know that stars by definition undergo nuclear fusion. Now you need to sort of pay attention to the fact that we're talking about fusion and not fission. So that's something we'll need to sort of, you know, make a distinguish between. But fusion, basically think of it as, you know, fuse. So you basically put multiple pieces together to get into one larger piece. All right. You put multiple pieces together to get one larger piece. And so as far as, you know, think of what your, what we said about the Big Bang, you end up with a lot of hydrogen. So one way of using fusion is to basically get hydrogen that we've got. And, you know, neutrons are flying around as well. And we can sort of put these two things together to get a deuterium. And we might release a bit of energy in the time being as well. So the key thing with the nuclear reactions is, as with any reaction, note that your reactions occur to basically become more stable. So your things undergo reactions to become more stable. And what does more stable mean? More stable basically means to reach a lower energy state. And that's why, if we've got your hydrogen and your neutron, we're saying that this has a lower energy state than these two separately, and that's why it's releasing a gamma ray as energy. All right. Now, the first question we might want to address is, where does this energy come from? Well, you might want to think back to what we said earlier about mass energy equivalence. And so what we're basically saying is that while there's not a huge difference, there is a difference between the mass of a hydrogen atom plus, or a hydrogen nucleus plus a neutron is slightly more than the mass of, you know, a hydrogen 2 nucleus. Now, this difference is not large. When you're trying to do these calculations, they will definitely give you the numbers, because you'll need quite a few decimal points because the difference is quite small. But it's important to note that this difference exists. And because this difference exists, it is due to the mass energy equivalence. It is equal to the E equals mc squared. That is, you've got a loss of mass. And due to the loss of mass, you will then get an increase in energy, or energy released. Okay. So this ties into basically Einstein's mass energy equivalence. All right. Now, so that's one option. Now, we might just quickly differentiate, because this is something that some of you have mentioned are things that confuse you. So we've just talked about fusion. So think of the word, I guess, fuse, right? To put things together. So you're putting multiple small things together into one bigger one. Whereas fission is you're basically splitting up. Okay. So this is, one large piece into multiple smaller ones. Okay. Now, both of these, for the reactions we're doing anyway, so both of them lose mass in the process. And that's why both of them release energy in the process. And therefore, as a result of that, both of them will use E equals mc squared to do so. So hopefully that makes it clear. Now, in case it's still unclear, fusion basically is what happens inside stars at the core. And that's generally what you'll be studying it with relation to. You've also got fusion occurring in the middle of, thermonuclear weapons. And whereas fission is kind of what we use for nuclear energy. I mean, in terms of what is available, obviously we're trying to do research on fusion because it's cleaner and so forth. So basically, your uranium, your plutonium, and so on. And, your atomic weapons. So basically the old nuclear weapons, so like think 1940s, is going to use fission. Okay. All right. So we'll need to talk about how we might be able to classify stars. We talked about this a little bit. So stars can be split based on their spectral type. And we've covered in previous topics about how you can tell the temperature of a star using Wieland's law and assume it's a black body. But it would also help you to sort of, I guess, know the special sort of, the sort of classification. Now, you can look this up, but basically you've got spectral types from like, O, and basically you can look up the specific temperatures. But basically these ones are higher temperature. These ones are lower temperature. And therefore the color, just due to sort of black body, is going to change, right? So the lower temperatures will look red, and then it'll kind of get, higher and higher. So this will start you looking yellow. And then, you'll start getting to sort of white because of effects that we won't get into. But basically, then it'll start just basically looking blue. Because, the peak spectrum starts getting sort of more and more UV, right? At this point, we see it looks blue because actually most of the light it gives off is in the UV range, and it doesn't really give off much of these colors anymore, relatively speaking. Okay. And so this is, you kind of will need to know these spectral classes. Now, some of you may or may not, I mean, I don't know if you've already remembered these, but I guess many students find this sort of hard to remember. So it might be a good idea to sort of try and find some sort of way to remember these if you're having trouble with that. And I guess the one that's often taught is, so O, B, A, fine, guy or girl, doesn't matter. And basically comma, kiss me. That's basically what people have come up with. Now, you may or may not like this, up to you, it doesn't really matter. You may prefer to memorize this directly, up to you, it doesn't matter. But you do need to come up with some way to recognize that from high temperature to low temperature, the spectral classes start from O, then B, A, F, G, K, M, right? You do need to be able to know this and identify the order, because you could very easily get a multiple choice question and ask you something like, okay, which of the following are correct? And they'll be like, okay, B is, low temperature. And if you know B is second, you clearly know B is not low temperature. Or, G is hotter than M, which is correct. Or I might say, F is blue. And if you know F is in the middle, you know it's not blue, and so on, right? So you do need to know that. But that's mostly a memorizing thing. And so that's what people have come up with. You can use it or not, up to you, but make sure you memorize that. Now, furthermore, on the classification of stars, another very important thing you need to know is your Hertzsprung-Russell diagram, often abbreviated as an HR diagram. And basically, you might have it being slightly different. You might have, it more or less represents the same thing, but you basically have two axes. Now, the axes here could either be temperature or spectral class. Right? Now, it's a bit, I suppose, different to normal graphs in the sense that if you're looking at temperature, higher goes on the left, lower goes on the right. But you could either have temperature or spectral class, but I suppose because we said spectral class depends on temperature, then, essentially it's the same thing there. And on this axis, you might be graphed, you might have absolute magnitude graphed, which is basically, the same as luminosity. Same thing, different scale, all right? It's a bit like saying, okay, I'll graph, concentration of hydrogen ions or pH. I mean, it's the same thing, just different scale. And unlike pH, they when one goes up, the other goes up. Wrong way, right? It is just like pH. I said the wrong thing. So when one goes up, the other goes down, all right? So, just pay attention to your graph. It's either absolute magnitude or luminosity on the, but look, whichever one you use, basically that way, it basically is brighter. And this way, it's basically dimmer. Oh, I shouldn't use brighter and dimmer just to avoid confusion with brightness, which is something slightly different. But basically, that way is more luminous. It gives off more light. And this is less luminous. All right? So it doesn't matter what scale they're using and what numbers they're putting, but upward is always, it gives off more light. Down is always, it gives out less light. It doesn't matter what scale they're using here, but left is always hotter and right is always cooler. All right? And you'll basically, just give you very rough ideas. You'll get this idea. You'll get this sort of main sequence. All right? So we've got the main sequence stars there. And that's, where most of your stars are. Anything that's kind of here means that it's not very hot, but it is actually quite bright. So we will call these your giants. And the reason for that is because, they are large. And the reason why we know they're large is because of the Stefan-Boltzmann sort of law, but we won't get into that. But basically, you know, if you've got a low temperature, but you're still hot, then the only way to compensate for that is you have to be big. So we won't get into the laws behind it. I don't think you are required to know the specific formulae for that. But even though, you know, this on the right-hand side is temperature and not radius, we know as a consequence of the fact that it's low temperature and bright, then it has to be large. All right. And then basically on this side, you're going to have your dwarfs. And very similarly, dwarfs, because they're actually quite hot, but they're not bright, then we know that, well, they don't give out a lot of power, I should say. They're not very luminous. Then they have to be very small. Okay. So those are basically your main sort of classifications here. Now, I've been sort of using the words, and I've been trying to be careful with them, but in case of any sort of confusion, luminosity refers to basically the power of the star, which basically is essentially intensity, but essentially it's, you know, how much energy the star releases, you know, per second, right? Because that's power, right? Power is energy per second. Okay. Now, brightness is referring to how bright the star looks to you. And normally we're measuring on Earth. So, you know, if think of a star as a light, right? If the light, you know, whether or not that light is far away from you or close to you, it's just as luminous as it was before, right? It doesn't matter, you know, where that light is. It's just going to give out the same amount of light, no matter where it is. Having said that, if that light is very far away from you, think of like a car, right? A car's headlights, it doesn't get, you know, it doesn't give out more light depending on where it is. It's just going to give out the same amount of light. Having said that, when a car is very far away from you, well, it doesn't look that bright, right? I mean, it's pretty dim. But as it gets closer to you, it gets brighter and brighter. That's not because the car, you know, has turned up its lights more or anything. It's just that the fact it's closer, so it looks brighter. Okay. And, you know, when you put your eye next to it, it's going to be unbearably bright. Even if I have some sort of very low power light, if I put it right next to your eye, it's going to seem very, very, very bright. So luminosity and brightness are different in the sense that luminosity is talking about how much power or how much energy that light gives out. On the other hand, you know, brightness is simply just how bright it looks to you. Now, for the same distance, the more luminous, the brighter. But, you know, brightness basically takes into account distance. And because your power is basically spread out over like an, you know, if you think about it, your sort of, you know, a particular thing is sort of spread out over a sphere. So, you know, you're actually basically taking your luminosity divided by 4 pi r squared is basically going to give you your brightness, because you're taking the amount of energy that your star is giving out and you're spreading it out over the surface area of a sphere. So, you know, higher the lightness goes, the luminosity goes, the higher the brightness. But, you know, obviously if we're talking about different distances, then it starts depending on the numbers. Now, these are the concepts, just like, you know, concentration of hydrogen is a concept. But a lot of the time, you know, just like concentration of hydrogen, you've got big ranges. Well, we also might want to have just some sort of scale that helps us figure out, you know, where these things lie without working with the actual numbers. And that's where, well, we introduce the concepts of absolute magnitude and relative magnitude. I don't think I tested on relative magnitude much in your course, but basically magnitude is a scale, again, a log scale that basically represents absolute represents luminosity, relative represents brightness. But basically that's what that represents. It's just a log scale of those things. That's why it's not really any different. Okay, so based on how bright or not bright the star is, and its temperature, which we can tell from our sort of what we did earlier in the earlier modules, based on black body radiation and, you know, using Wien's law to work out the temperature, we can then work out how big the star is. And, you know, we can then kind of work out, you know, the star life cycle. And we basically figure out that, well, you know, you've got different types of stars. So we've got your main sequence stars. So main sequence stars are basically, you know, undergoing nuclear fusion, and they're basically converting hydrogen to helium. And then, you know, that's basically, think of it like, if you think of it as a human, that's your human in their adult life, right? You know, they're not growing anymore. You know, you've got your child becoming a adult kind of aspect. And that's kind of when a star's trying to start forming, and that's all the gas trying to sort of form together and all that. But once it starts going, it's kind of like an adult. And that's where it spends most of its life. But of course, you know, people get old and they get into old age. And well, you know, old age for stars can have sort of different sort of situations. But, you know, red giants is when they're starting to get a little bit older. And basically when you start fusing helium to carbon, okay? Your hydrogen to helium is still continuing. I'm just saying though, that at this point in time, your helium is starting to form into carbon. Now, if you have supergiants, which are basically just, you know, if we want to add them onto the graph, they're just bigger, hotter versions of the same thing. So they're just kind of here. So the same thing, but they're still, again, bigger sort of versions of it. Then your supergiants will then be fusing, well, basically successive fusions until iron. And this relates to your, basically the fact that iron, as far as, you know, your course is concerned, has the lowest binding energy, or I should say highest binding energy per nucleon. In other words, it's the most stable nucleus. So if you recall what we said earlier, your star, you know, fuses things together to, you know, make things more stable. So hydrogen became helium because helium nucleus is more stable. Helium then becomes carbon because carbon's more stable than helium, and so on and so on and so on. But once you get to iron, which is like number 26, I think, then you've already reached the most stable nucleus. And so if you were to go up with fusion, then you're not actually gaining energy. You're actually going to be using up energy to do it. And so the star won't do it. Okay, so it has to stop there. And that's, by the way, and just giving you a very sort of, you know, so iron is like here. This is helium. That's why hydrogen to helium is quite easy, because it's, you know, certainly a very stable one in sort of around it. That's kind of why anything smaller tends to undergo fusion, and anything bigger tends to undergo fission. Because if you're bigger than iron, what you actually want to do is not become bigger, which is worse for you, but become smaller to become more stable. This is sort of binding energy per nucleon, right? So this is atomic number So, you know, how big you are, and this is, you know, binding energy. And basically, you want your binding energy to be as high as possible. So your course basically says iron is the most stable. There are some challenges to that, but let's ignore that for now. And basically, your star, therefore, starting here, will fuse until there. And then, you know, there's not much point continuing, so it won't continue. Whereas if you're starting somewhere here, like you're doing with the uranium and plutonium, you're kind of splitting up to go this way. And in both cases, you're actually becoming more stable. And therefore, in both cases, you're releasing energy. Okay. And so that's your supergiant. And basically, it's doing the next stages. And depending on how big your supergiant is and, you know, how hot it is, then, you know, it decides how far it can go. And then you've got your dwarfs. And so your most typical is your white dwarf. You might have also heard of things called brown dwarfs that I don't think you need to get into. But basically, these are just, you know, they've got no nuclear reactions left. So these are basically stars that are essentially just, you know, you can either think of them as already dead or they're just waiting to die. You know, these are sort of old age, and this is, well, you know, comatose, right? So basically, your white dwarfs are stars that they used to be stars, right? They used to be a main sequence star that became a red giant, and well, the red giant lost its outside, and the core is a white dwarf. But there's no more nuclear reactions happening anymore, and basically, it's just going to cool down over time. So think of this as a very, very, very hot. So we know we're talking easily over, like, you know, it's very hot. I mean, many, many, many thousands of degrees. But basically, think of it as something that's very hot, and it's just getting cooling down over time. And, you know, when it cools down to nothing, then obviously we're basically just saying it's going to, you know, we're saying it's going to die. Okay. Now, what basically happens with stars depends on its mass. So, you know, these are all content that, you know, you could review, but hopefully, you know, the fact that we're covering it makes it a bit easier for you when you read it. So basically, you've got a main sequence star. Now, a main sequence star will ultimately become a red giant, okay? When it's kind of entering old age, all right? But then what can happen is, well, it can either undergo, you know, what become a planetary nebula. So basically, it will just blow off its outside shell. And then once it loses its outside shell, it'll become a white dwarf, as we mentioned earlier. And so because, you know, you lose, and there's sort of radiation pressure and, you know, blowback and things like that sort of decide this. But basically, there's a fair bit of, you know, theory and math that goes behind why we're saying this is the case. But basically, a white dwarf is the core of a red giant, but you've lost the outside. So basically, you know, yeah, they threw away the outside layers. They threw away the clothes, and you're left with the middle bit, all right? So that's one thing that could happen. The star could get bigger, and then it could lose the outside shell to a planetary nebula and leaving only the very, very, very tiny part inside. Or the other way that it could go if it's very big is it could undergo a supernova. And a supernova is going to need a very, very large amount of mass. So your mass must be, let's say, greater than, you know, 8 solar masses. So M0 refers to the mass of a sun usually. Normally, like, there's a dot in between, right? And if it undergoes a supernova, it's basically like a big explosion, all right? So lots of things get blown off, so you lose a lot of mass. And so a lot of our, you know, so this is very energetic. And so there's, you know, lots of mass is lost and ejected into space. And so, you know, a lot of just stuff is lost. And that stuff then, you know, obviously gets recycled and goes through the process again and makes perhaps a new star or, you know, a planet. And so it's very possible that, you know, Earth, for example, and lots of other planets are a result of, you know, just left over from a supernova. But basically, it's just, stuff is just thrown out, leaving, bits inside. But what's, because you started with so much, what's left actually could be quite a lot. And what you could get is what's called a neutron star, all right, which include pulsars and so on. Or it could become a black hole. This entirely depends on whether what's left is heavy enough. So basically, if your core is greater than, let's say, 3 solar masses, then it can become a black hole. If your core is less than 3 solar masses, then it won't, and it'll become a neutron star. And, there are different sort of, limits that we can talk about here, but I don't think they're really required in your course. So best to leave those for you to look up if you're interested. Okay, so back to your Hertzsprung-Russell diagram then. What we're basically then saying is that because I won't label the axes here, because the axes will essentially be the same. So we'll just call it an HR diagram. You'll recognize that's your main sequence. We'll recognize you've got your giant groups here. And you'll recognize you've got your sort of white dwarfs here. And basically we're saying that it depends, we can kind of predict what's going to happen to a star based on, well, its mass. So you could get something that kind of goes like this. It could kind of start here, and then it could become bigger, and then it kind of just dies, all right? So you could get something like that into a sort of white dwarf, and, then it just gets cooler and so on. So it cools down. Or you might get something that's relatively large. So if it's something that's relatively large, it's sort of, okay, it starts fusing a bit, so it starts heating up, and it stays here for a while, it becomes a sort of giant, and then it is not big enough to be at a sort of, supergiant, so it goes to a white dwarf, and then it starts cooling down again, all right? Or alternatively, you could have something like, something that's really massive, and so it just goes, okay, I'm a massive star, and I'm going to die really quickly. I'm going to supergiant, and I'm going to make a few sort of turns here for, and then, basically blow off into a supernova. All right. So basically, you've got these sort of different outcomes that your star could sort of follow here. Okay. And that basically gives us, remember, the stars undergo fusion. So stars have fusion in the core. So that's why, they turn hydrogen to helium, to sort of make those things up. But essentially, they make up our elements. So basically, we're saying for elements up to iron, we're basically saying they're due to just normal nuclear fusion in your sort of, in your stars. And for elements that are greater than helium, with an atomic number greater than helium, greater than iron, I mean, we needed a supernova to do them. Okay. And that's basically what we're talking about there. Now, you will need to know your sort of proton-proton chain. And you do need to know their sort of, you don't need to necessarily know their numbers, but you do need to know the equation. So you've got a proton plus a proton, and those will form together to give you a deuterium atom. Okay. And it, releases a bit of energy. Then, that happens twice. And you'll basically get this and plus another one. And this will also release a bit of energy as well. And then because both of these will happen twice, basically we need these to sort of happen. And once you happen, then your final thing that happens is that these two join together to give you a 4He2 plus 2 of the hydrogen atoms plus energy. And so that's why we're saying the net result, because if you look at this, right, you've got, this happening twice. So this needs to happen twice. And, when you have that happening twice, what you're basically going to end up getting is that you're going to basically have these, basically cancel them out, just like you do with a chemical equation, all right? And so that's why you're going to get your basically 4 hydrogen. They're going to become a 4He2. Because these two will cancel out with those. So ultimately, you can go and balance those equations out, but ultimately, 4 of these will turn into 1 helium. Okay. Because you need to memorize these equations, perhaps it might be helpful to sort of show you what I mean. I'll leave out, I suppose, when I balance it, I'll leave out sort of these things. So we need that, and we need one, we need to then take this. And then we need to take the second one of these. Right, we need to add these together to give a 4He2. All right, so how do we get that? Well, I guess we just more or less mirror everything we did earlier. And well, how do we get that? Well, to get that, we had to do, So that really means we've got, 1, 2, 3, 4, 5, 6, right? Those two become that. So, 1, 2 there, 3, 4, 5, 6. You've got 6 of those things reacting to get, 2 of these, which becomes that. And there's a 2 there. So basically, that's what I'm saying. Ultimately, you've got 4 of these becoming 1 of those, right? So hopefully that makes sense. So that's basically your sort of net result. Now, that will basically take it through to the main sequence kind of star. Now, as far as the red giant goes, it depends on the sort of size of the red giant and so forth, but basically it comes down to the radiation pressure. And basically as you lose fuel, because remember you're using up hydrogen, and because you're using up hydrogen and getting more helium, at some point you're going to run out of fuel. So just think of it like think of it like a car. You're going to run out of fuel. So as a result, when you start running out of fuel, you're basically not going to be able to keep up the fusion. So you end up trying to, instead of burning petrol, you end up burning whatever you got when you have. So basically what ends up happening is you're going to have, helium plus helium. And basically then that will give you your beryllium plus gamma. And this basically is what starts happening. And then you've got your 8 beryllium, plus 4He2 to give you, your carbon, right? And this basically is what happens in red giants. And basically, you can then take this carbon and basically, introduce that even more. All right. Now, you also need to know the Cno cycle. Now, the Cno cycle, as you might suspect, stands for carbon, nitrogen, oxygen. Okay. Now, carbon, nitrogen, oxygen cycle basically is, you can look up the equations, all right? Because, I mean, look, I could write them out, but I think it's probably better for you to look them up. One, you'll know them a bit more, but secondly, I think you just, you're having trouble if you have trouble with this, you might be understanding what they mean. And if I just write it out again, it won't help you. So what I want you to understand ultimately is that the Cno cycle still converts hydrogen to helium, basically, overall. Okay? So it's basically just another way. So you've got the proton-proton chain, which I kind of, showed you, right? Now the Cno cycle will have different equations. It'll have different equations, but it's still basically converting hydrogen to helium. So we're just talking about, another process that a main sequence star that is hot enough, if hot enough, you need to be at a certain temperature to be able to do it. But if you're at a hot enough temperature, and that relies on if you're big enough, if you're at a hot enough temperature, then basically you have the Cno cycle available to you, which basically means, you have another option. The result is the same, but you end up doing it faster and cheaper, kind of. In other words, it's essentially catalyzing the reaction. You are making the reaction, which is still hydrogen to helium, ultimately go faster. All right. So basically, you end up with different pathway to get to the same end. You are literally just catalyzing the reaction. Okay. So you do need to know the existence and how it works, but basically Cno results in you going through this process faster. And as a result, that's why, or part of the reason why anyway, that your stars that are hotter have a shorter lifespan, because they end up burning that fuel faster, because they will burn it up through a Cno cycle as well as, proton-proton. But, Cno cycle will do the most of it. Okay. And, that's basically how you get your elements. Your elements are a result of fusion in the middle of stars. Depending on how big the star is, will also decide how far it goes in terms of nuclear fusion. If it's big enough, it will go all the way to iron, but it won't go any further as far as the fusion part goes there. If it's small enough, it might go, a bit further, but it might not necessarily go up to iron, right? But iron is the ultimate step, right? Once it gets to iron, it won't go any further. And to go further, it's not really fusion in the star. It's just, when the star undergoes supernova. Okay. Does anyone have any questions with that?